Okay, we're back in Module 7, and we're going to start Part 2, which deals with sampling distributions. First, a little bit of a review. Uh, Throughout this course, we have talked about various population parameters. For example, we've talked about the mean of a population, mu. We've talked about the variance of a population, sigma squared. And actually, in this chapter, we're going to start talking about population proportions as well. Many times, people are interested in the proportion of a population that has some characteristic, such as what proportion of people will vote for a particular candidate, or a firm might be interested in what proportion of customers see their advertising campaigns, and things of that nature. Every time we've had a parameter of a population, we also have a corresponding sample statistic. When we talked about mu, we then talked about x bar, the sample mean. We talked about s squared, the sample variance. And in this chapter, we're going to introduce p bar, the sample proportion. So notice, as I said, every time we've had a population parameter, we kind of have a corresponding sample statistic to go with it. Now, one thing that's different about parameters in statistics is parameters are treated as constants in statistics. That is, there is a true population mean, mu, which we assume is a constant. However, statistics are random variables. They're going to vary depending on which items go in the sample. For example, I often use this example in class. Let's say I've got a class of 30 people, and there is some population mean height to the 30 people, mu. Supposing I was going to take a sample of 5 students and look at their sample mean height, x bar. Well, I'd get a different value depending on which 5 people go into my sample. One sample of 5 students might give me an average height of 5'10", another sample of 5 might give me an average of 5'8", and so on. So that is, there's an entire distribution to a statistic. And that distribution is called its sampling distribution. So getting to some definitions here. A sampling distribution is the distribution of all possible values of a statistic from every possible sample of size n from the population. For example, the first sampling distribution we're going to take up is the distribution of x bar, the sample mean. That would be the distribution of all possible sample means from every possible sample of size n from the population. Now, in most cases, we're not actually going to go out and try to take every possible sample. Most statistical work is based on a sample. The important thing about sampling distributions is you have to realize that the values you get for your statistics came from these sampling distributions. So it's going to help us to know something about those sampling distributions. In general, there's going to be 3 things we want to know about a sampling distribution. We want to know something about its mean, something about its standard deviation, and do we know something about its shape? I am going to give you a simple little example here where we're actually going to look at the entire sampling distribution because it's going to be a very small one, just as an illustration. Imagine the following. Imagine I had a population of numbers that just consisted of the values 1, 2, and 3. Nothing else. Like having a hat with 3 numbers in it. Number 1, number 2, number 3. I'm going to take a sample of 2 of those 3 numbers with replacement. That is, I'm going to pull one of those numbers out, look at it, put it back, and pull another number out. Here's every possible sample that I could get. I might pull a 1 out the first time and a 1 out the second time. Or I might get a 1 and then a 2, or a 1 and then a 3, etc. There are 9 possible samples here. I'm going to take the average of these samples. In other words, I'm going to calculate the sample mean. The numbers 1 and 1 have an average of 1. 1 and 2 have an average of 1.5. 1 and 3 average to 2, and so forth. Now, let's go back to the population for a moment. We had the numbers 1, 2, and 3 as our population. What would be the mean of those 3 numbers? Well, if you just average 1, 2, and 3, the population mean here would be 2. Notice something else. If you calculated the mean of all the sample means, which would mean we would add them up and divide by 9, so we have 9 sample means here. If you add those up, I bet they add up to 18. And if you take 18 divided by 9, you will get a mean of 2. In other words, the average of all the sample means was equal to the same value as the population mean. And that gives us our first important principle here. In fact, this will always be the case that the average value of x bar, in other words, if we average all the sample means, we get the population mean. They're the same number. And we will make use of that quite a bit in upcoming modules. Next, we need a formula for the standard deviation of x bar. Now this one won't be as intuitive as the mean just was. The formula we're going to use is that sigma x bar is equal to sigma, the population standard deviation, divided by the square root of n. By the way, sigma x bar, and I think I have this on the next slide, but sigma x bar is referred to as the standard error of the mean. Generally, the formula we're giving you here holds true if you're sampling from an infinite population or when the sample size is small relative to the population size, generally no more than 5%. There is an alternative formula to use. If you're sampling more than 5% of the population, you need a correction factor, sometimes called the finite population correction factor. You would take sigma over the square root of n, which we had before, and you'd have to multiply it by the square root of n minus n over n minus 1. But to make life simpler, we're just going to use the first formula. We're just going to use this one. And actually, that's not too bad of a simplification, because if you look at this correction factor, in most cases, our sample size, little n, is small relative to the population, big N. For example, if a pollster goes out before an election and takes a sample of 500 or 1,000 voters, that's a very small part compared to the entire population, which might be in the millions. If you do this mathematically and think about it, if little n is small relative to big N, then n minus n over n minus 1 is pretty close to the number 1. And of course, the square root of 1 is 1, and it would just drop out of the formula. And we'd be left with the formula that we have here. So we will use generally what I call the simpler formula. Sigma x bar is sigma over the square root of n. And as I said before, sigma x bar is called the standard error of the mean. Next, we need to know something about the shape of the distribution of x bar. It turns out that the shape is often normal in many cases. I'm going to give you two cases here. You can prove in mathematics that if you were sampling from a normal population, or nearly so, then the distribution of x bar will be normally distributed. Again, that's provable in math, but you don't have to worry about the proof. Now that's okay, but that's not really the interesting case because most of the time a researcher goes out and gathers data, they might not know if they're sampling from a normal population. So what if the population is not normal or its shape is unknown? Well, there's a very important theorem in statistics called the central limit theorem that we can rely on in this case. Basically, what the central limit theorem says is that the sampling distribution of the sample mean, x bar, approaches the shape of a normal distribution as n, the sample size, increases. And this occurs regardless of the shape of the population. Now, there's a certain vagueness to the central limit theorem. It simply says as n increases. As a general rule of thumb, a sample size of 30 or more is generally sufficient to assume that the distribution of x bar is normal. So what that's telling us here is the following in terms of graphs. We have some population x with some mean and some standard deviation. We might not even know what the shape of x is. But now we're interested in a new distribution. We're interested in x bar, the sample mean. It's actually like a new population. It's the population of all possible sample means. We've learned three things. First of all, the mean of this distribution right here is exactly the same as the mean of the population. That's why I've kind of lined them up on top of one another here. The standard deviation of this distribution is going to be the population standard deviation divided by the square root of n. Lastly, according to the central limit theorem, we can assume this distribution is approximately normal, provided that the sample size is 30 or more. By the way, here's an example from a website. that shows you an illustration of the central limit theorem. Down the left-hand side here, we have 4 different populations with different shapes. Here we've got a uniform distribution, here we've got a bimodal distribution, here we've got a skewed distribution, and here we have one that's fairly normal. It then shows you what does the distribution of the sample mean x bar look like for n equal 2, n equal 10, and n equal 30. And by the time you get to n equal 30, all of these sampling distributions have a very familiar symmetric bell shape to them. In fact, some of them are even getting more bell-shaped by the time you get to n equal 10. So that's why the central limit theorem is a very powerful and important theorem. It doesn't matter what the population looks like, the distribution of the sample mean gets more normal as n increases. Why do we care about all this? Let's kind of stop for a moment and say, why do we care about the distribution of x bar? In future modules, in fact in the next module, we're going to want to try to estimate an unknown population mean mu. If you don't know the mean of a population, it seems logical to start by taking a sample and calculating your sample mean x bar. But how close will x bar be to mu? That is, how much sampling error will there be? Well, in order to answer that question, we need to know what the distribution of the sample mean looks like. And if we know it's normal, that'll really help us because we know that on a normal distribution, for example, there's a pretty high probability of being within, say, a couple standard deviations of the mean. So that all comes later. For right now, we're kind of assuming that we know what the population looks like. We know sigma and mu, and we're learning about x bar. In the next module, we'll change that. We'll start to change that around and say what happens when you don't know the mean. Now, we can do something that is similar to something we've done before. We now have a new normal distribution. X bar is normal with n bigger than 30. Any normal variable can be converted to the standard normal in order to solve probability problems. Remember how you convert things to the standard normal? You take the variable minus its mean over its standard deviation. So to convert x bar to z, you take x bar minus its mean, mu, over its standard deviation, sigma x bar, and note that that's sigma x bar, not sigma. And you can convert this to z and therefore answer probability problems. So let's do a couple sample probability problems and distribution problems. Assume the population mean ACT score last year was 21 with a population standard deviation of 5.2. So I'm describing the population there for you. I'm telling you the population ACT is 21 and the population standard deviation is 5.2. And suppose we take a sample of 36 students who took the test. First, I'm going to ask you to just describe the distribution of x bar, the sample mean. That is, whenever I ask you to describe a sampling distribution, I want to know those 3 things. What is its mean? What's its standard deviation? And do we know its shape? Then secondly, I'm going to ask you a probability question. What's the probability that you will get a sample mean of the 36 students to be between 19 and 23? Let's start with the first part. Describe the distribution of x bar. Well, we already have formulas for the mean and standard deviation, and then we can apply the central limit theorem to get the shape. Given that the population mean mu is 21 and sigma is 5.2, we know that the expected value of x bar, or its mean, is equal to the population mean, and that equals 21. Sigma x bar, the standard error of the mean, is sigma over the square root of n, which would be 5.2 over the square root of 36, which turns out to be 0.866. And what do we know about the shape? Well, with n of 36 exceeding 30, we can apply the central limit theorem and assume the distribution is normal. So this is what we know so far. Here's the population of ACT scores with a mean of 21, standard deviation of 5.2. But we're now interested in the distribution of the sample mean. Its mean is exactly the same as the population mean. E of x bar has got to be 21. Sigma x bar is sigma over the square root of n, which we just calculated to be 0.866. And lastly, by the central limit theorem, we're going to assume this distribution is normal because our sample size is sufficient. Now, the second part of the problem said find the probability of getting a sample mean x bar from 19 to 23. Well, how do you calculate probabilities on any normal distribution? You convert the values to z-values, much like we did earlier. The key thing here is remember you're converting x bar to z, not x the population, but x bar. So we want the probability that 19 is less than x is less than 23. You convert those to z-values in the following way. Take 19 minus the mean of 21 over the standard deviation of 0.866. Take 23 minus 21 over the standard deviation of 0.866, and you will get z-values of plus or minus 2.31. Go to your table or use your calculator. Look up the cumulative probability of 2.31 and subtract off the cumulative probability at negative 2.31, and you will get a final answer here of 0.9792. That is, you have better than a 97% chance that you're going to get a sample mean between 19 and 23 if you take a sample of 36 students concerning the ACT score here. Let's take a look at this graphically. Again, here's our distribution of x bar. Normal with a mean of 21, standard deviation of 0.866, and we want the probability from 19 to 23. We're going to answer that by converting these to z-values and then looking up the area. So here's the conversion process. X bar is up here now, and here's our z distribution. 19 converted to a z-value of negative 2.31, 23 converted to a z-value of 2.31, and the probability in that interval we just calculated a minute ago was 0.9792. Let's do one more example of the distribution of x bar, similar to the one we just did. Assume that the population mean life expectancy in the U.S. is 80 years of age, with a population standard deviation of 12 years, and we take a sample of 64 people. Describe, once again, similar to the last problem, I ask you to describe the distribution of x bar, that is, what's its mean, standard deviation, and shape. And secondly, I ask you a probability question. For a sample of size 64, what would be the probability that the sample mean would be within 3 years of the population mean? Let's do part A again first. Given the population mean is 80 and sigma, the population standard deviation is 12, we know that the mean of x bar, or expected value of x bar, is 80. Sigma x bar, the standard error of the mean, sigma over the square root of n, is 12 over the square root of 64, which is 1.5. Once again, a sample size of 64 is large enough that we can assume the central limit theorem holds, and the shape of x bar is normal. Now in the second part, the probability part, we want the probability that the sample mean is within 3 years of the population mean. Well, since the population mean is 80, within 3 years of that means anywhere from 77 to 83. So what I'm really asking you then in part B is find the probability that x bar is between 77 and 83. Again, we solve this by converting to z-values. 77 less than x bar less than 83. Do the conversion process, subtract the mean and divide by the standard deviation for both of them, and you will get z-values of plus or minus 2. 77 minus 80 over 1.5 is negative 2. 83 minus 80 over 1.5 is positive 2. Go to your table or use your calculator. Get the cumulative probability up to 2, which is 0.9772, and subtract off the cumulative up to negative 2 of 0.0228, and the answer is 0.9544. So there's better than a 95% chance that you would get a sample mean life expectancy between 77 and 83 under these circumstances, with the sample size of 64, and assuming the population mean is 80. Again, let's take a quick look at this graphically. I first described the population to you. The mean was 80, the standard deviation was 12. Again, we might not know what that distribution looks like, but we don't need to know in this case. We're interested in the distribution of the sample mean, x bar. Its mean is exactly the same as the population mean of 80. We calculated its standard deviation to be 12 over the square root of 64, which is 1.5. And then in the second part of the problem, I wanted the probability from 77 to 83. So we're going to get that probability by converting to z-values. 77 converts to a z-value of -2. 83 converts to a z-value of +2. And the area under the curve between those 2 points is 0.9544. And that's the end of part 2. And next, we're going to do something very similar to what we just did, but with a new sampling distribution. We're going to take up the sampling distribution of the sample proportion.